We're working in section 5.2. I have two more examples I want to show you. Let's go right to example number 5, and let's begin by writing the equation in matrix form. In the first row we have 1, 1, 2, and in the second row we have 2, 2, 5. And Gauss-Jordan method says we should start in the first column and make a 1 on the diagonal. It's already there. And so the next step is to make a 0 off of the diagonal. And so that's this 2 right here in the first column. How do we make that into a 0? We're going to multiply -2 times row 1 plus row 2. The first row stays the same, and the second row becomes 0. And then actually we'll get another 0. -2 times 1 is -2 plus 2 is 0. And then -2 times 2 plus 5 is 1. And so this is different from any matrix we've seen before. The big difference is that we have all zeros on the left-hand side. And so in order to make sense out of what this means, then let's just go ahead and convert that second row back to an equation. What does that equation say? It says 0 times x plus 0 times y is equal to 1. The left side simplifies to 0. We have 0 is equal to 1, which is a contradiction. So we can say that the system is inconsistent, and we can say there's no solution. It might be tempting to try to get a 1 here in the second column on the diagonal, but that's not possible with the Gauss-Jordan method. And in theory, we could get a 1 there, but that would change the values that we already found before, in particular this 0 here in the first column. And so we can't make a 1 here without undoing the work that we already did here. It should be clear that that's reasonable. When we go and we look at the equation, we see the system is inconsistent. It's not going to be possible to make it consistent by doing some other operation. There's one other thing I want to point out. It's possible that the entire row could be zeros, that we could have a 0 over here on the right hand side as well. And then what would that mean? That would give us 0 equals 0, and that would lead us toward a dependent system and an infinite number of solutions. So for sure in this case, if this were a 0, then we would have an infinite number of solutions. That sort of leads us right into the next example where we'll see a dependent system. Actually, in example 6, we're pretty confident this system will be dependent before we even begin the problem, and the reason is because there are more variables than there are equations. There are 3 variables and only 2 equations. We saw an example similar to this in section 5.1, and it would be good for you to look back at that example and compare it with what we're going to do right now with matrices. In theory, this system could be inconsistent as well, but as it turns out, it won't be inconsistent. It will be dependent equations. So let's see that. So let's get started. Let's write our system in matrix form: 2, -5, 3, 1, 1, -2, -2, 8. It's this Gauss-Jordan is the same procedure every time. It's to start with the first column from left to right, get a 1 on the diagonal, and then zeros everywhere else in that column. And then just repeat that procedure in each column as far as we can go. So that's what we'll do. Where this 2 is, we need a 1. We could multiply the first row by a half, but a different way to do it, another way to do it, would be to just switch the 2 rows. And the nice thing about that is we would avoid some fractions here. So let's just switch row 1 and row 2. And that gives us 1, -2, -2, 8, and 2, -5, 3, 1. Still in the first column, we need a 0 where the 2 is. We need to multiply -2 times row 1 plus row 2. The first row stays the same. And the second row will be 0. And then let's be careful here with the arithmetic. -2 times -2 is +4, minus 5 is -1. -2 times -2 is +4, plus 3 is 7. -2 times +8 is -16, plus 1 is -15. Okay, so we finished the first column. We can go over to the second column and make a 1 on the diagonal. That would be this -1 here. We multiply by the reciprocal of -1, which is just -1. -1 times row 2. The first row we can just copy down. The second row will be 0, 1, -7, +15. And we have a 1 on the diagonal. Let's go ahead and make a 0 off of the diagonal. We're still in column 2. A 0 off of the diagonal is right here with this -2. How do we do it? 2 times row 2 plus row 1. I'm going to copy down the second row since it's not changing, and then right up above it I'll write in 2 times 0 plus 1. Keeps the 1 that we already had, that we got a long time ago, and we want to keep it there, so that's good. 2 times +1 is 2, minus 2 is 0. That's the 0 that we're trying to get. 2 times -7 is -14 minus 2, which is -16. And then 2 times +15 is 30, plus 8 is 38. Okay, so we finished the first 2 columns. We go on to the third column, but wait a second. In the third column, what are we supposed to do first? We're supposed to make a 1 on the diagonal. And that's not possible because there aren't enough rows for the diagonal to reach that third column. And so we just stop right here. We've gone as far as we can. We're going to convert each row of the matrix back into an equation and see what we have. The first row says 1 times x plus 0 times y. I won't write that, that cancels. Minus 16z is equal to 38. And the second row says 0 times x, cancels, plus 1 times y, minus 7z is equal to 15. And so, sure enough, we have dependent equations. And remember in section 5.1 we learned that one of the variables should be set arbitrary, and we should solve the other variables in terms of the arbitrary variable. Well, when you look at the equations that we have, which variable should be arbitrary? Z should be arbitrary because it shows up in both equations. And if we solve for x in the first equation, we get x in terms of z. We could say 16z plus 38. And if we solve for y in the second equation, we get y equals 7z plus 15. So z is the arbitrary variable. We have x and y each in terms of z, and we can go ahead and write our answer. Remember, the answer should be an ordered triple. And so for x, we're going to write the expression in terms of z. And for y, we're going to do the same thing. And then z is just z. And we might even put the braces around it to indicate that's the set of all ordered triples where z is any real number and then x and y follow from z using these two little formulas. So here's our answer. We're finished with the problem. It might be nice to take one more step and or a comment, one extra comment, and just say, what are some particular solutions? The solution we have here is rather abstract. We talked about this in section 5.1. We can get particular solutions if we just pick a value for z and then plug it in. So z can be anything. Let z equal to 0. What is x then? I bet you said 38. I bet you would say y is 15. And of course, z is 0. Or perhaps you would choose z equal to 1. I bet you would say 54, 22, and 1. And of course, you could do this as many times as you want for as many values of z as you want to get as many particular solutions as you want. It might be fun to take one of these solutions like 38, 15, and 0 and plug it back in to the original equations. If you plug in those numbers for x, y, and z, you'll see that both of these equations are true. Okay, before we wrap this up, let's just go one more time through example 6. We wrote a matrix. We saw there were only 2 rows but 3 variables. It didn't bother us a bit. We worked in the first column first and got a 1 on the diagonal and then a 0 off of it. Then we went to the second column and we got a 1 on the diagonal and a 0 off of it. And then that led us to this matrix right here. And from there we said we've gone as far as we can, so it's time to go back and to the form of equations. It's time to rewrite each row as an equation, and then we can solve both of those equations in terms of z, and we can write our answer just as it is in the box. That's all for section 5.2.